Hi, so we have our second talk this afternoon, and this is going to be by Shigui Ruan from University of Miami, and Professor Roxana Lopez Cruz is going to present him. Thank you very much.
Thank you, Ms. Teresa. Good afternoon with everybody, and good afternoon, Shigui Ruan, because of your participation in our event. Well, I'm going to introduce you. Dr. Shigui Ruan is currently professor in the Department of Mathematics of the University of Miami. He's master and bachelor in mathematics from Central China Normal University. His doctor in applied mathematics from University of Alberta, Canada, under the guidance of the great mathematicians, Dr. Irving Friedman. His research interests include differential equations, dynamical systems, and mathematical biology. He's expert in some topics like the center manifold theory and Hopf bifurcation in semilinear evolution equations, multiple parameter bifurcations in delay equations, and traveling waves in non-local reaction diffusion systems, which have significant applications in biology and medicine. Finally, he has authored of many research articles, books related to mathematics. He has an H index of 75 with more than 20,000 citations. It's a pleasure for me, Dr. Shigui Ruan, and please begin with your talk. We are going to be delighted with this.
Rosanna, thank you so much for your introduction, for your kind invitation, for Juan, for your arrangement. It's very nice to see you guys virtually. And you know, Miami has the Institute for Americas. Hopefully, some of you will come to visit Miami, so I will be able to see you personally in the future. We're gonna have a meeting next summer. Okay, so so today I'm gonna talking about spatial-temporal dynamics in epidemic models with Levy Flight. So a approach that is called Fractional Diffusion Approach. This is based on a paper with my former postdoc, Professor Zhao at Nevada. It's published in the JMPA. Okay. It's really nice to link it to this Central South America communities. Okay. So I'm going to give some introductions. So I think the motivations are more interesting. So what is, for example, what is the motivation for the problem? What is my own motivation to consider this kind of problem? And once you understand that, and then the learning part becomes a little bit easy, but that becomes mathematical. I'm going to introduce the so-called susceptible infectious susceptible models with fractional diffusion and talking about the math. And later on, I'm going to give some simulations to show you and give a brief discussion. So to start with that, so we are talking about diffusion. Of course, we started from the Brown motion. I recall that when Brown studied the problem in 1827, he was basically looking through a microscope at the pollen of a plant inserted in the water. So these small particles in the water move very regularly, you know, and then after some time they settle down. The distribution of those particles is very nice, and this is a very nice property. But it was very hard to understood, you know. So in other words, a group of particles spread as a whole according to irregular motion at each particle, but settle down regularly, which is a Gaussian distribution. The first person who understood the problem properly was Einstein, who published a paper in the Annals of Physics in 1905. So his idea is that he modeled the motion of pollen particles as being moved by individual water molecules, because at that time there were some doubt about the existence of molecules and so on. So Einstein was trying to study the problem, try to prove that, you know, molecules and something exists. Anyhow, so his conclusion, of course, he ended up showing that assume there are n particles at a location, say you choose a location as the original location, x equals 0, at the original time t equals 0. At a certain time, the probability of distribution at a time t at a location x is given by, as we know, this function. This is a well-known function. And then Einstein proved that this function happens to be the solution of the heat equation with the division coefficient D. So since then, the Laplacian operator has been used to describe the Brown motions. So in other words, Einstein gave a link between the Brown motion and the Laplacian operator described the heat equations. So you can see this is the Gaussian distribution. Okay, this is well known now.
Professor, we are not seeing the slides. I don't know if we are moving them.
Yeah, can you see that?
I only see the first one, and I think some of our colleagues are doing the.
Oh, you mean the slides? I'm still in the same slides.
Ah, okay, perfect.
So can you see? Can you see
show that? And okay, thank you.
Can you see the indicator?
Yes.
See your
Okay.
first slide, don't worry.
Yeah,
It's
I'm
the
still in the
first
first
slide.
slide.
Okay.
So, but looking back, you reconsider the Brown motion. So looking at this diffusion equation, so you look at carefully the time steps and the step size and time size are all small because they were considering the movement of small particles in a very small time scales. So in other words, compared to this space and time, the heat equation describe or the Laplacian operator describe any local diffusion. Okay, so local diffusion. But that's been a question for a long time. How do humans move? Because after Einstein's work, people using heat equation Laplacian operator to describe the Brown motion of humans, many species, many animals. But do humans move randomly following a Brown motion? This is a question, okay? And this becomes very interesting. So what are the mobility patterns for humans? This is a question borrowed the scientists for a long time until 2006. In 2006, there's a paper published in Nature by a group of 3 scientists from Tübingen, somewhere else. So the group of people, they collaborate with banks, okay? So they selected 4 cities in the United States, 1 in New York, and then in Jacksonville, in Florida, a small city in the central, I think it's here in the middle part, and then Seattle. So what they did is that they worked with the bank. They asked the bank to, remember 20 years ago, people still withdraw money from the bank. On the bank notes, in each note, there's a stick saying that when you receive the money, you report your postcode through a website. Okay, so after a certain time, they received like more than 1 million reports. Okay, so the circulation of more than 464,000 bank notes showing that in New York, for example, almost 60% of people use the money within 10 kilometers, because the indication says that, well, initially the money was initially from the bank here, and somebody withdrew the money and used the money within 10 kilometers, which is the distance, roughly the distance for us from our home to where we work, right? That's basically true. But also they found out that about 7% of people use the money 800 kilometers away. Some even use the money in other countries. So they put the data, they found out that if you choose the distance of those people as a distribution, they found out that's not a normal distribution, that's not a Gaussian distribution. In fact, there's a Levy flight. In other words, around 60% of people move locally in short distance, but there's a small fraction of people moving long distance. This is a very surprising paper. After that, there's a very large number of papers published in Nature. People follow the same idea, try to do similar observations. For example, in 2007, there's a group of people working studying, animals like bumblebees and deers and albatrosses, they found out their movement, their trajectory is a Levy flight as well. And there's another group of people working on the mobile phone data of 100,000 people and found out the trajectory is a Levy flight. And it's the same thing for marine predators and T cells that go inside. And the hunters, that you have a few hundred hunters. Most of the hunters, like you move in a group, there's a few of them go to a long distance to try to stay away with the big group. The same thing. So in other words, there's a very large number of papers published afterward finding that most animals and humans trajectories are not a Brown motion. In fact, it's a Levy flight. So Levy flight, that's a random walk in which the probability distribution is heavy-tailed, like a constant times x to the power a fraction power. So this is the figure, depends on the constant. Majority move locally, and there's a small fraction of people looking long distance. And even like in 2015, there's a survey here. Quite a few hundred papers were reviewed and found out that Levy walks in physics and biology are very common. So from this experiment, we can see that the diffusion patterns of humans and many biology species, in fact, are local plus non-local. So local is not enough. So in other words, heat equation property is not enough to describe a human movement. So you can see here, this is the first figure is the random walk, right? And the second one is the Levy flight. So you move locally and then non-locally and then locally and then a long distance. So this is more reasonable, more realistic to describe our movement as human beings. Okay, so then mathematically, how to model the non-local diffusion? In fact, there are two ways to do that. One way is using the convolution integral operators. So using convolution, okay, k star u minus u. So this is the integration term. So the first term describes the movement from everywhere else to here, to this location. The second term indicating individuals from this location moving to other places. So the idea, in fact, came from Kendall in 1957 when he was studying epidemic models, and he thought that in order to consider how many people are infected, you needed to consider all those movement on those people. When somebody came from another place to this location, that individual, in fact, could infect other people on the way. So to model that properly, you have to integrate from the beginning location to the current location. Peter Bates wrote a survey paper showing that this kind of non-local equation appears in material sciences in 2006. And in 2007, I wrote a survey showing all kind of non-local epidemic models. And then later on, there's this is a very famous book published by American Mathematical Society, Non-Local Diffusion Problems in 2010. So there are also biological models, for example, the virus infection model, the competition
sorry, are we
models.
still in the first slide? Sorry.
You're still in the first slide?
Okay. Yes, yes.
Yes, you are in the first slide.
No, I'm in the seventh slide.
No.
Oh, so probably can you stop sharing and share again, because we don't see, we just see the first slide. Okay, now it's yes, it starts moving.
So I cannot use the full screen.
The first screen, yes, the first one.
Can you see now?
Now we are seeing the 8th slide.
The 8 slides.
Yes.
Also, you missed all those.
Yes. But
I'm sorry. Okay. Okay. Anyway, this is the Brown
Yes.
motion. So that's what you saw.
Yes, this is the topic. Mhm.
Okay, that's okay. Sorry, then I didn't realize that. Okay, so this is the paper published in Nature showing the Levy flight, the bunker notes.
Exactly.
This is the more references here. showing publishing in Nature about the Levy flight. Okay, this is the probability. So this is the figures of the Brown motion and the Levy flight. And
Again,
No,
that
we are
is
not
we are
not seeing the
seeing
figure
this.
there.
oh, okay. So how about small one?
Now it's
This
okay.
one- yes, now
okay.
there's the random walks and okay.
Oh, I'm sorry.
Logical
Okay.
mobility. Yes.
So can you see that? If I don't use,
We can see this one, and then you go one to one. In such
okay,
a way.
let me make it a little bit bigger.
Yes.
Then that means if I use the full screen, it will
Maybe
not
you can
move.
see. Yes. Okay. Mhm.
Is it better now?
Now it's okay. Biological mobility. Mhm.
Yeah, okay. So, okay.
We
I'm very
understand.
sorry about that.
Don't worry.
Oh, yeah, I mentioned that there's quite a few papers published in Nature to support the claim that the humans and many biological species move following a Levy flight. These are all the references. And this is the Levy flight, the Levy distribution, a Levy flight. Okay. How about now?
That's okay.
It's okay now, right? Okay. So this is the graph for the random walk and the Levy flight. And this is the first diffusion, the first method to model the non-local diffusion using convolution integrals operators. Okay, this is the references, especially the one, and probably many of you know this group's work, right? Okay, now let's move to the second method. That's the one I need to talk. Okay, if you missed the first, now it's okay now. Okay, you can see that now, right? Okay,
Yes.
the second method to model non-local diffusion is using fraction Laplacian operators. So there are different approaches to do that. So the first one is so-called the Fourier approach using the pseudo differential operators. That means you have a Laplacian operator and you take the fraction power, you take in the Fourier transformation, you end up this formula. You can use this method to define the fraction Laplacian operator. The second one is called hypersingular integral operators, because this is the integration on the space. As you can see, u of x minus u of 1, but you have x minus 1 in the denominator. So there's many points there x equals y. So this is called high singular integral operator. In fact, this is a very common one. This is the one used very commonly. But we use a slightly different approach, which is called a semi-group approach. So again, delta is the Laplacian operator. So e to the at is the semi-group. Okay, is the semi-group. The semi-group acting on u minus u divided by t to the power 1 plus s, then integrate from 0 to infinity. Then you differentiate respect to s. Remember, s appears here, divided by the gamma function. Then we define this one as the fractional operator. Well, you have different ways to define that. So just a remarks here. Maybe some of you know this fractional Laplacian very well. Some of you maybe it's not so familiar with that. Just recall that we are talking about Levy process, and this guy, the negative delta to the fraction S is the infinitesimal generator of a Levy process. So that's why this is this form has been used to characterize the fractional Laplacian. Secondly, looking at for any real number x, we define a function x plus and s. Now, if x is positive, use x. If x is negative, then use 0. Then this s will satisfy this arithmetic problems or Laplace elliptic equations. This equation is given by c to the absolute value of x to negative s when x is negative, otherwise it's 0. So that's you can see there's x to the s. Well, recall in the figure here, the function we used to describe the Levy flight, the distribution you have to access to the negative fraction power here. So that's why we use this one to define the Laplacian fractional Laplacian operator. So this is the way, okay. And this kind of problem has been, this kind of equation have been studied by many researchers. The classical references is starting from around 2000. There's some papers by Cavalieri and his group. And this book, in fact, Cavalieri was awarded the Abel Prize. And this paper, in fact, was mentioned in this citation. And there are other papers on this aspect. And also there's a monograph, a short monograph published in 2017 by Springer. Also, there's some specific biological models using Laplacian, fractional Laplacian operators. For them, but these few papers are talking about the traveling waves of future KPP equations with Laplacian, fractional Laplacian operators. Especially the first one showing that the traveling waves, the speed is completely different from the standard KPP equations with regular Laplacian operators. And also there's some work about Allen Kane equations. Also they are scalar equations. And other people try to propose Data-Cavalterra kind of systems like competitions. The last two were more like numerical results, no mathematical analysis. So you can see mathematically and biologically, fractional Laplacian operator have been used has been used to model real world problems, and there are also some theoretical studies on this kind of equations. So my motivation is kind of interesting. First, Rosanna mentioned that I graduated from Central China Normal University. In fact, that's in Wuhan. Now everybody knows where Wuhan is. Wuhan is right here. So this is the map of the Hubei province. Wuhan is here. So there were highways from Wuhan to almost other cities in the province, right? And Wuhan is in the center of the country. Hubei is in the center. That's why it's called the Central China. Wuhan has equal distance to Shanghai and Beijing and Hong Kong and Xi'an. It's right in the middle. So take faster trains, you can reach the big cities in 4 hours. And there are flights to almost any cities in the country, to the west and to the east and so on. This is Wuhan. You can see that it's right in the middle. And also, before the pandemic, there were international flights to all continents in the world from Wuhan. So you can see this is an ideal location for traveling. But in other words, in the worst case, in the scenario for pandemic, this is the worst place you could have, because this is, in fact, that's what happened. If we don't talking about the origin, you're just talking about the starting of the pandemic. So this is really what happened. So the local movement of those people spread the virus to other cities in the province very quickly. And there were travelers to other provinces, then by highway, by flight, they travel very quickly within a day to all provinces, and then also internationally. So in other words, the local movement induced the spread of the virus within the city, and non-local movement spread the problem to other provinces, other countries, and other continents. So once the virus is spread to other cities, for example, for Europe, in Spain and Italy, when they were established there, and the process repeated. Okay, this is a repeated process. So in other words, the pandemic is caused by the local and the non-local movement of the human, of the host. But how to model such local and non-local spread of infection diseases? You know, during the pandemic, there were like at least 10,000 papers on modeling COVID. My colleague asked me, with any new mass from the modeling. Okay, I thought about that. Most of people using either, most of the time, 99% use ordinary differential equations. A few of them use reaction diffusion equations. But as I mentioned, reaction diffusion equations only describe local diffusion. While for COVID, it's really a combination of local and non-local. So how to model that? So I was wondering for a long time to see how to do the problem. And then I went back to the paper I mentioned published in Nature 2006, which he described, which he found out that, the human movement, in fact, were local plus non-local. At the end of the paper, it was very interesting. The last paragraph of the paper read as follows, quotations. To our knowledge, that this is the first empirical evidence of such an ambivalent process in nature. We believe that this result can serve as a starting point for development of a new class of models for the spread of human infectious diseases, because universal features of human travel can now be counted in a quantitative way. Because they found out the movement non-local is a Levy flight. The Levy flight can be described mathematically. So from that point of view, they believe that you can build a new class of infection disease models, which is more realistic. So that motivated me to think, maybe I can use Levy flight to the fractional diffusion to describe the epidemic models. So that's my motivation. The motivation is from two sides. One side, I came from Wuhan. Okay, my wife was there when the pandemic started, so I was following the news every day. And then also I'm a modeler. I'm working on modeling infectious disease. So that motivated me to think about something which might be a little more realistic. So this is our result. So to make things a little bit easy, we only consider two classes of populations. The susceptible population, which is given by U of X and T. So that's the density of the susceptible population who are not infected yet at the time T and location X. V is the portion of those individuals who are infected and infectious at a location X and time T. So of course you need a certain domain. The domain is a bounded domain with a smooth boundary. And then assume that you have two diffusion rate, du, dv for the two subpopulations respectively. And also we have the fraction, okay, the si for the two subpopulations, S1, S2. They both are between 0 and 1, okay? And they are fraction powers corresponding to the Laplacian operators here. And this is the normal realization of the Laplacian operator in a suitable function space. So we propose the equation as the following, the model as the following here. So the partial derivative respect time plus the spatial, okay, this, as I mentioned, this describes the local plus non-local diffusion with fraction S1 here. On the right-hand side, the first term, that's the growth, the population, okay, that's like the logistic growth, okay, AU minus BU squared. And B describe the intra-species competition, like I just mentioned. The first two terms describe the logistic growth of the population. And then this term, the third term on the right-hand side describes the interaction between the susceptible individuals and the infectious individuals. So this is U plus V is the total population. So this is a kind of frequency, okay? Depends on how often you interact. So P is the interaction rate or the infection rate. And for Q is the recovery rate. So that means, recall, some people will infect it a second time, even third time. So this is for the V. Similarly, for the infectious population, you have the partial derivative respect T and the Laplacian non-local Laplacian operator, and the interaction between these two groups gives you new infections, but some of them were recovered. and it becomes susceptible again. So this is SIS, because the IS, once you infect, it becomes susceptible again. Also, you need 2 initial conditions when time equals 0 at the beginning. What is the initial distribution? What is the initial density of the non-infected people and infected people? Of course, that depends on the location. So this is the model we proposed, a simple model. Okay, of course, we need to make certain assumptions here. The D here, for example, the D we just mentioned that this D is defined by the semigroup method. But if we know the eigenvalues and eigenfunctions, eigenpairs, then you know the fractional operator can also define out of the series here. Okay, and if there's no disease, of course, the population follows the logistic growth. In other words, A is going to be the growth rate, and B over A is the carrying capacity of the environment for the population. We mentioned the P and Q already. P basically is the transmission rate or the infection rate. Q is the recovery rate. All the coefficient depends on X, so they are function of X. So we need a certain assumption on the continuity. We assume that their whole continuous in a sense is between Lipschitz continuous and uniform continuous. Of course, those coefficients are non-negative. Recall that when the fractions S1, S2 are equal to 1, then the model becomes the standard, the rational diffusion equation, okay, which has been studied by many others, like I mentioned a few here. So now we want to see when S1, S2 are between 0 and 1, what kind of properties we have for this epidemic model. Before doing that, we needed to introduce certain notations. We use U greater than or equal to V means greater due to, but not equal. Okay, and you have the wage means the maximum. You can see this is the minimum. So when the number is greater than 0, this is positive. Then this is okay, the same thing. So this is very important. Now, if W is L1, then we define the average. You know, I mean you take the integration. So this is the average. This is very important. We're going to use this notation throughout the whole talks. Okay. Also, we have the sublimited space. Also, we have the bilinear forms. Okay, using the K here. Well, K is given by this integration. Okay, let me skip that. So for any problem, the first thing we are concerned is about the equilibrium point. Okay, so that is the elliptic equation. Okay, there's another terminology called the basic reductive number. For an epidemic model, the basic number is the average number of infection one person can infect. For example, you have a community, nobody has a disease, but you have somebody who carries certain virus or bacteria or whatever enters the community because the disease is infectious. So that individual is going to infect other people. Then during the time when that person is sick, on average, how many people that individual will infect? So that number is called the basic reproductive number. Now, if that number is less than 1, that means the individual infect at most 1 person. Of course, you can control the disease. If that number is greater than 1, that means in fact, say 2 or 3, then you can see you're going to have epidemics. So we're going to study this one. Okay. So before doing that, let me list the assumption again. So the coefficients are C alpha, since they hold continuous. Also, for the growth rate for the population, of course, the average is positive. You know, otherwise the population is going to die out. So for the model, we just mentioned that the basic reductive number can be given in terms of the variation form here, which looks a little bit complicated, but this is the bilinear forms that we just defined. The Laplacian, the fractional Laplacian operator appears here. So you look at carefully, P is the infection, Q is the recovery. So for any infection disease, the basic reduction number basically depends on the infection rate, the recovery rate. It's always like that. So now we try to estimate that. So the first result here, so we can estimate the basic reduction number. So it has a low bound. The low bound is the average of the infection rate divided the recovery, average is the recovery rate. The upper bound is you consider the ratio of infection rate over the recovery rate. You take the supreme, okay? Also, I mentioned that this R1 is greater than 1 and less than 1 is very important. That if we know the principal eigenvalue of this one, okay, then the sign, the principal value and the sign of 1 over R naught minus 1 is going to be the same. So in other words, as I mentioned that if R naught is greater than 1, okay, then you don't have infection disease. So the principal is going to less than 0. If R naught is less than 1, then, I mean, it's less than 1, is you don't have the problem. But R naught is greater than 1, you do have that problem. So the next one, it gives you more specific estimate for the R naught. So when the average of the infection rate is greater than the recovery rate, R naught is greater than 1, which makes sense. When the two are equal to each other, then R naught is less equal to 1. Well, otherwise, it's going to be less than 1. Okay, so we can say something about the basic reduction number. So in other words, how we have two bounds, lower bound and upper bound. The next result told us when the division rate approaches 0. Okay, what does that mean? Biologically, that means that just like during the COVID, there are lots of quarantines, lots of restrictions, lots of stay-home orders. That means very few people are moving. In that case, the basic reduction number can be used. We can use the upper bound to approximate the basic reduction number. On the other hand, when D approaches infinity, that means you are open. Okay, when you are open, you know the population is uniform. In that case, you can use the low bound to approximate the R naught, which is going to be a constant. Okay. Now, how about the basic reduction depends on the fraction S? Well, we needed to know a little bit more. If we know the second least eigenvalue of the operator, then R naught is non-increasing in S. So we know certain monotonicity in that one. So the result can be proved by using results we obtained in another paper, which Zhao and I we still not published yet. It's a singular port-based eigenvalue problem for the fractional Laplacian operators. Okay, I'm just mentioning some idea here. So for the epidemic model, after we obtain the basic reduction number, the next question you would like to see is the existence and the stability of the equilibrium point. So we're going to have two types of equilibrium point. One is called disease-free equilibrium point. That means nobody is infected. Okay. The second one is the endemic. That means you have certain people infected. So for this problem, each one is a standard continuity assumption, and R naught is less than equal to 1. In this case, we don't have a positive equilibrium, but we do have a disease-free equilibrium point, which is U1 0. That means you do not have anybody infected. Well, the U1 is nothing but, remember, this is a logistic equation. So U1 is a solution of this one. Okay. So on the other hand, when R naught becomes larger than 1, then you do have a positive equilibrium point. Okay, you have positive equilibrium point. But we just don't know what the positive equilibriums are, because that's the eigenvalue problem. That's the elliptic problem. But in the constant case, okay, if those averages satisfy the property, in other words, the growth rate, the average of the growth rate is greater than or equal to the average of the infection rate is greater than equal to the recovery rate, then you always have a positive endemic equilibrium point. Okay. Then the next question is how we don't know how to evaluate the equilibrium point, but can we approximate? In other words, when the D takes different limits, what the equilibrium point is going to change. So we try to answer that question. So we can look at the problem from two different ways. The first direction is the inference of the division rate. Okay, so when du or dv approaches 0 or approaches infinity, when du approaches 0 means that people are not infected, do not move. You try to restrict the movement. Say this is, if this is the case, if R naught is greater than 1, then we know there's a positive equilibrium point, right? And the result, this result shows that then the positive equilibrium point, U and V, can be approximated by U naught and V naught. U naught and V naught are solutions of this algebraic equation. Okay, this equation. So in other words, we can approximate the equilibrium point when du and dv approaches 0. So you can do the same thing when dv approaches 0, which is more realistic because during the pandemic, those are infected either stay at home or isolated. Okay, so you can obtain a similar result. The next result is what happens if the du or dv or both of them approach infinity? That means you do not put any restriction on those people, on the movement of those people. So again, so in this case, when we assume that the average of P is greater than the average of Q, again, we have a positive equilibrium from U and V. In this case, when dV approach infinity, then the positive equilibrium from U and V can be used U infinity and V infinity to approximate, and U infinity and V infinity are solution of this equation. The most interesting case is like this one. When du and dv approaches infinity, right? In this case, of course, this complete uniform, complete mixture. So, of course, the infected people is going to approach this value. Okay, so that depends on R naught. Okay, and just give you an idea. When COVID started in Wuhan originally in the beginning of 2020, R naught is roughly 3, which is very high. But later on, when the virus mutate, it becomes Delta and all kind of. And eventually, 3 years later, when eventually China was open doors, at that time, when they opened doors, even before the new year, everybody's moving. So the whole country was infected within a month. Because at that time, R naught was roughly 22. You can see this is very, very important. R naught is much larger when you later on when the virus the viruses were more infectious later on. So the next question is about the result we mentioned that is about the existence of the equilibrium point and the approximation of those equilibrium point. And how about stability? Okay. Recall that to study the stability, we need to make sure that the solutions of the model exist globally. So we need to go back to the model again. This is the model we mentioned. We needed to let me very briefly mention a couple of things here. So okay, anyhow, we can show that when the initial values are non-negative, then the model, the initial boundary value problems of the initial value problem have a unique global solution. So in this sense, we can talk about stability because the solution is globally. Also, the solutions are positive, and also they are bounded. Okay, they're bounded. So in this case, then we can see that the solution, you have a global attractors. Then we try to prove that in each case, either the disease-free equilibrium is your global attractor or the positive equilibrium point is attracted. So the first result shows that when R naught is less than 1, we have a disease-free equilibrium point, right? And this result shows that in fact this guy is globally stable. The reason is the proof is based on again the global existence solutions and the boundedness, also the existing eigenvalues. Now remember, the second component equals 0. Basically, you reduce the first. It's just a scalar equation, which is the logistic equation, the KPP equation. Of course, you have global stability, right? So the second result here for the positive equilibrium point, remember the coefficient all depend on x. There's almost no way to obtain global stability if the coefficient are time space dependent. So we need to assume that the coefficient A, B, P, Q are constant. Also, the growth rate is greater than the infection, greater than the recovery rate. In this case, if that is the case, you have a positive equilibrium point, which is globally stable. Okay, and surprisingly, the proof of the result is just constructing the Lyapunov function. That is very standard, the Lyapunov function. We can show that in this case, the positive equilibrium is stable. So also we did some simulations. For example, in the one-dimensional case and the two-dimensional case, we choose different initial values. So the fraction S1, S2 are both 0.6. And because we have the fraction, so the du, dv 0.8 to the power 1/06 and 0.7. So the key here, P equals 0.3, that's the infection rate. Q is 10, that's the recovery rate. So P is less than Q. So you have a disease-free equilibrium, which is 2.0, is globally stable. In the one-dimensional case, we choose initial value like that one. On the two-dimensional case, you choose initial value like two-dimensional, depending on X and Y. So this is, you can see the global stability of the boundary equilibrium point, or the disease-free equilibrium 2.0. And in the second case, okay, in this case, we choose Q to be 0.2, which is less than 0.3. Of course, then you have a positive equilibrium point, 2 and 1, which is globally stable. So we can do the simulations and show that global stability convergence. Okay, to summarize, okay, spatial movement is the key factor for the spread of infection disease as we experienced during the pandemic. All the disease spread from one place to another because the host moved. Okay, so the classical reaction diffusion equations with Lyapunov operators have been used extensively to model the spatial spread of infections. But as I mentioned, that those models only describe the local spread. Okay. Well, in the modern time, we travel on different scales, from a few kilometers to a few thousand kilometers, or in 1 day. Okay. I don't have any negative opinion about using reaction diffusion regularly. What I'm trying to say is that the classical reaction diffusion equations only describe the local movement, local spread. For non-local, as I mentioned, because especially I give you a series of papers in Nature showing that the mobility pattern of human, in fact, is a Levy flight. In other words, like 80% of people move locally, about 20% of people look long distantly. So based on that factor, with that observation, so we proposed a simple epidemic model with Levy flight using fractional operators. So one thing I would like to emphasize is that during the pandemic, all the countries try to protect them, cancel flight and forbidden boat crossing. And people always worry about the disease transmitted for high-risk areas to low-risk areas. But if you're talking to those people who are doctors or epidemiologists, they knew that, in fact, it's the other way around. Usually, it's they're looking back. When we travel, how many of us, when you travel, you do not come home? You always come home. Our travel are a return trip. So the pattern is that, in fact, the people from the low risk area travel to the high risk and bring back the virus and so on. So it's always like that. So it's two-way. Travel is not one direction. It's two directions. Okay. The risk is from low risk to high risk and then to low risk areas. So as I mentioned, I mentioned the motivation, especially my own motivation. So we proposed the model, this published in the journal, and then we, at that time, we think that this is the first piece of theoretical study on epidemic models using fractional diffusions, and the referee believed that too. So that's the paper was accepted. So, but we didn't. We mentioned COVID, but we think the model can be used to calibrate some of the data if somebody have the data, but we didn't do that. We hope somebody else, knowing how to do the simulations and know the data, could do that. So let me just stop here. Thank you very much.
Thank you, Dr. Shigui Ruan. It was an interesting talk. Si tienen alguna pregunta, la pueden hacer al chat o abrir sus micrófonos. If you have questions.
Sorry
please.
for this.
Don't worry.
Sorry for the problem at the beginning.
It was my fault. Okay, because I understand your article. I read your paper before.
Oh, okay.
I know about this. Okay.
Can I ask a question?
Okay.
Sure.
Yes, you can.
Okay. Thank you for this talk. It's very interesting from the mathematical point of view, and I see that really it is motivated by the pandemic and trying to by the end, we hope to use the model to simulate and to predict. And I have one general question concerning the real validation, which means data. And
Yeah.
another question, it is really something that I'm interested in. How can you make the right choice of the fractional derivative? Okay. I mean, when we go to the practice point of view, we have to choose S1 and S2.
Yeah.
How can you go with this?
Well, so we have results there. So that's, in fact, this is a very good question. In fact, if we knew those theoretical studies, the fraction is very important. A half is a critical value. It's very subtle, but we have a result showing here. They are not. Some properties depend on S. Once you know.
Yeah, of course.
Yeah.
Yeah.
Then you.
Yeah, I really appreciate this kind of a priori estimator, but and behavior. But in the practice, I mean,
then if you try to simulate certain data, then how to choose this S properly to see the data? Then I don't know. Then you need the real data to combine with the real data to make the right choice of S.
I think,
what exactly they'll be.
So,
Certainly that's a really good question. Yeah.
Probably we need to run some kind of inverse problem and.
Yeah, exactly.
Okay,
exactly.
thanks. Thanks for the talk. Thanks.
Thanks. Some other questions? Okay, we have a question, Dr. Shigui Ruan. How do you define the R0? Yes. And
Yes.
define R0 in base of your model using fractional diffusion. Is it the same way? This is not the same way that we used to do this with the next generation method. Yes.
It is the same. If you reduce this one to ordinary differentiation, that would be exactly the same.
Okay.
Yeah.
But the question of the others people
you don't see that. Yeah, don't see that directly. Yeah.
You have to check this. This is a good alternative for everybody who is working with the PDE systems for this kind of spatial terms in the propagation of epidemics. Then I always has a question about the fractional point of view to select this kind of model. Well, today I have one of these, and the other question also is going to help us in such a way to use it to make the election with the data. This is the hard work to go in this way, but I think that the theory is very interesting for us to begin working with this with all people who is working in epidemic model. Okay, there is questions in the chat. Could you see Dr. Shigui Ruan? It's from Samir Wujan. Technical question, he says.
Okay.
Yes, you can see this, Dr. Shigui Ruan, or Samir, if you want, you can make the question.
Let me see here. No, I cannot see that.
Okay,
Yes, I can ask the question.
Yes,
okay.
You can.
Thank you for this nice presentation. My
hi.
question is sort of technical. How do you deal with the nonlinear term that maps L2 to L1? Since you have when you are working in L2 space and you have this product, and also u squared to the power of u to the power of 2. So you have a nonlinearity that maps in a larger space, L1. Yeah, yes, exactly, in the system.
Oh, in the system here.
Yeah, for the well-posedness of this equation.
Oh,
because
I
here
think no, the sense was later on here. No, I think I forget exactly what the here. You mean here?
Yeah.
Yeah, we
so you're working in L2 or L1? Yeah. The phase space.
No, but into L1 here, this is TS. This is the this is not for the equation. This is for the operator. This is for the operator.
Okay.
Yes, it's the operator. It's not the whole equation. No, it's not the whole equation.
Okay.
Okay.
Yeah.
I still don't see the phase space. What is the phase space? Like the state space. Sorry.
The space. Okay, let me see here.
Okay, it's either L2, I guess, or L1 or C.
I see. I think it just depends either or depends on what yeah.
Because if it's L2, I think there is a problem in the definition of the nonlinear term.
Yeah. So you can see, I try to cooperate it so that either it's in C or in L2.
Okay. Maybe for the nonlinear term, there will be a domain where the nonlinearity goes to L2, I guess.
Yeah.
And another question, if I may ask,
yes,
it's about the disease equilibrium when the coefficients or the parameter depends on space. What is the difficulty in constructing this disease equilibrium? Because in the stability, you assume that you have the parameters are constant, does not depend on space.
You see, any equilibrium problem will be the solution of this equation number 2.
Okay.
And even we can't find them.
We can find
no.
Okay.
I try to say that we can approximate the equilibrium point.
Okay.
But if the second one equals 0, then that would be easy because that's the KPP equation.
Yeah.
For the positive one, we even cannot find it. But if their coefficients are constant, then we could find it.
Yeah. Okay, thank you so much.
Yeah.
Okay, thank you, Samir. Another question? Okay, thank you, Dr. Shigui Ruan, for your nice presentation, and we hope that you will be as soon as possible in South America or in Peru.
Yeah, sure.
Okay, see you, Dr.
Yeah, sure. Thank you so much, Samir. Thank you very much. Yeah.
Luz Teresa?
Yeah. So let me quit.
Thank you very much to Elias Cueto and Shigui Ruan for their